Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering. So far in in this subject, in this topic of material science, we have covered the mechanical properties of materials. Okay, all the discussions, mostly all the videos, they revolve around mechanical properties. But if you watch the introductory videos related to material science, I told you that there are various engineering properties of materials which are considered before for their selection for various application purposes. Engineering is basically the application of science for to make life easy for various designing of various you know apparatus, instruments, buildings, whatever, for construction, whatever, they're vast use, biomedical, whatever it is. So we have to consider various properties, engineering properties of materials. So mechanical is one aspect. We discussed various mechanical aspect, various mechanical properties of materials. In the next series of videos, we'll be discussing thermal properties of materials which are related to heat and temperature, that aspect, the thermodynamic aspect. So, like I said, every branch of engineering, branch of science is interrelated. Every branch of physics is interrelated. So here we will discuss some concepts related to heat, temperature and thermodynamic properties. So we will not go into as much detail as we do in the thermodynamics subject, but we will discuss just the important bits, the important parts which are necessary for material selection. Okay, so we know that there are various properties of materials which are used, which are considered for engineering applications. So there is the mechanical properties, there is the thermal properties, the chemical properties, the electrical properties, magnetic properties and optical properties. So we have discussed mostly the mechanical properties. Okay, there are a lot of other properties as well, but I thought, why stick with just one aspect? We will include all of them. We'll discuss all of them bit by bit. Okay, so in the next series of videos we'll be covering some of the thermal properties, okay, the thermodynamic aspect. So like we'll also discuss chemical, electrical, magnetic and optical properties in future videos. Okay, so what are the thermal properties of materials? Basically, as I said, thermal properties, they revolve around two important aspects. It is basically thermodynamics. Okay, so it revolves around two important things. Everything revolves around two important things. There are a lot of other things, but the basic thing, the foundation upon which this thermal properties is built upon, that is heat and temperature. Okay, so the thermal properties, they basically tell us how different materials, they respond to different levels of heat, different changes in temperature, what effects they show, how they respond, so that we can judge how they will behave in various external situations, which determines their suitability for various engineering and practical applications. Okay, so depending upon their thermal behavior, we have to select appropriate materials for different purposes. For example, let's say you are a very basic example, let's say you are building a furnace. Okay, and obviously it has to tolerate extremely high temperatures, several thousand degrees Celsius. So you have to select appropriate materials accordingly. First you have to determine how much temperature, how much high temperature we need to to build this furnace so that it can withstand that temperature. Then what is done is that always a margin of safety is given. Suppose the maximum temperature which the furnace has to be designed for is 1000 degrees Celsius. It is always taken to have some safe side 200 300 degree plus, So a furnace is designed with 1300 degrees Celsius. So appropriate materials are chosen. This is just one example. There are many examples. So this is what a basic example of evaluating the thermal property of a material is. Okay, so the basic thermal properties which we'll be discussing, this is not the entire list. There are a lot of subcategories. This is just the basic foundation. Okay, so some important thermal properties which we'll be covering, some important topics on this. They are heat flow and temperature, thermal expansion of materials, specific heat capacity of materials, latent heat, then change of state of materials, calorimetry, all that. Then melting point and boiling point, modes of heat transfer, emissivity, absorptivity, thermal conductivity, thermal resistance, heat current, all that. Okay, so this is not exhaustive in itself. This is just some of the key properties I've just chosen to show here because of lack of space. This is the main gist, the crux. We will build upon this layer by layer. Okay, this is the foundation. Okay, so as I said, most of the thermal properties, it revolves around two important things: heat and temperature. Basic foundation thing. So what is heat? So let's say you stand near a fire, okay, a log of fire. You feel warm. In a winter season, a winter night, you are standing near a fire, you feel heat, you feel warm. Okay, because the heat, the energy, it flows from the fire to your body. Suppose you stand close to a freezer, okay, near ice, you will feel cold, cool. This is because heat is flowing from your body towards the ice. So if you see, in the first case, heat is flowing from the fire towards your body. But in the second case, the heat is flowing from your body towards ice. So there is a change in direction of heat flow. In this case, it is from left to right, because you are standing on the right side in both cases. So in the first case, left to right; in the second case, right to left heat flow. Why this change in direction? So the main thing that determines the direction of flow of heat is temperature. We'll discuss that in this video later on, but for now you understand that heat always flows from a body which is at a higher temperature to a body at a lower temperature. In this case, in the first case, the fire is at a higher temperature, your body is at a comparatively lower temperature. So heat is flowing from the fire to your body. In the second case, your body temperature is higher than that of ice. So heat is flowing from your body towards the ice. Okay, so this is the basic concept. Now, the heat, this entity, this thing, whatever it is, this form of energy, it produces in us the sensation of hotness or coldness. So how can you define heat? What is heat exactly? So there are two theories on heat, on the concept of heat. First is the caloric theory. The second one is the dynamic theory. So in the caloric theory, it is theorized that heat is an invisible, weightless and odorless fluid called caloric. Okay, this is the hypothesis. This is the theory. This is the statement that heat is an invisible, weightless and odorless fluid. You cannot see heat, yes. You cannot measure its weight. You cannot smell it. So heat is a invisible, weightless and odorless fluid according to this theory. So when some caloric or heat is added to a body, its temperature rises, and when some caloric is removed from the body, its temperature falls. So that is self-explanatory, because heat always flows from a higher body temperature to a lower body temperature. So here is another important thing which we'll discuss later on, but I will introduce it here briefly. So let's say there are two bodies. Okay, let me choose the pen. Okay, let's say we have two bodies. Okay, it is body A, which is at temperature TA. This is body B, which is at temperature TB. Let's say body A is at a higher temperature than body B. So obviously heat will flow from body A towards body B. So when heat flows from body A outside of body A, it is losing heat. So obviously its temperature will decrease. And when heat is flowing into the body B, its temperature will increase. So how long will this increase and decrease go on? Till both the temperatures of bodies A and B, they become equal. This is called as the situation of thermal equilibrium, when both the bodies are at the same temperature. So when a body loses heat, its temperature drops. When a body gains heat, its temperature increases. And this cycle, this process goes on till both the bodies are at the same temperature, and this situation is called as thermal equilibrium. So this is the caloric theory, but it had some disadvantages. It couldn't explain certain phenomena, such as when we rub two objects, if we rub our two hands, it gets warm, we produce heat. So the basic production of heat by friction, this theory, it failed to explain that. How does we generate heat out of nothing by just rubbing our hands? So this theory was replaced by the dynamic theory of heat. So according to the dynamic theory of heat, all substances, solids, liquids and gases, they are made up of molecules. Okay, let's say we have any object. Here I've taken a cube just for the simple analysis. It is made up of molecules, and these molecules, they are always in random motion, continuous random motion in every direction possible. Okay, now depending upon the temperature and nature of the substance, the molecules, they may possess three types of motion: translatory, vibratory and rotatory. Translational motion, vibrational motion, rotational motion. Okay, so in translational motion or translatory motion, the molecules, they move in a straight line. Okay, they move in straight line. Let's say, just to simplify it, we consider the three axes x, y and z. Okay, this is the three axes. So molecules can move in straight line in x-axis, in y-axis and z-axis, also in the negative z, negative y and negative x, but in straight lines. Okay, it is always straight line. It can also move like this, somewhere in between like this. Okay, it's not necessary that it follows only x, y and z. This is just to show you, but it will always move in straight line motion. Okay, that is translatory or translational motion, and it is common in gases, mostly gases. Then we have vibrational motion or vibratory motion. Now this is kind of to and fro motion. Okay, to and fro motion, just like simple harmonic motion. Okay, simple harmonic motion. The molecules, they move to and fro. In one case they will move towards each other, then they will move away from each other, then again they will move towards each other. So they always oscillate, they always vibrate about a mean position. Okay, and there is always a fixed gap, equilibrium separation between them. Okay, which we also covered in the in the mechanical video, where we discussed the elastic behavior of solids. So there is always a fixed separation gap, but they always move to and fro about a mean position, which is a fixed separation gap. So this is vibratory motion, which is common in liquids and gases. So simplest example is to visualize simple harmonic motion. Okay. If you want more on that, you can watch the waves and oscillations playlist. Then we have rotatory motion. So as the name suggests, in rotational or rotatory motion, the molecules, they rotate from one position to the other. Okay, from one position to the other, rotation. Okay, like this, it goes on and on from one axis to the other, about a fixed axis which passes through the centers of the molecule. Okay, from one position to the other, rotation. So there are three types of motion: translational, rotational, vibrational. And it is because of these three types of motion, the body, the object, it possesses certain internal energy. Okay, certain internal energy. It is the internal energy of these molecules because of their continuous random motion, and this internal energy is called as heat. Okay, so when a body is heated, these molecular motions become fast. Okay, their kinetic energy increases because their velocity increases. So heat is basically an energy of molecular motion, which is the sum total of the kinetic energies of all the molecules because of their translational movement, vibrational movement, rotational movement. So heat is internal energy of the body because of their movements: vibrational, rotational, translational movement of molecules. That is called as heat. That is heat. Now, heat, you cannot define heat in isolation. This is the thing here. It can be a bit difficult to catch for the first time, but try to understand. Heat in itself has no meaning. You cannot say what is the heat content of this body. You cannot say something like that. It is defined in terms of temperature. You need temperature because heat and temperature, they're kind of cause and effect. One is nothing without the other. The other has no significance without the other part. They always work in pairs, heat and temperature. So when there is a temperature difference between the two objects, there is heat transfer. So what is this heat transfer? It is basically part of internal energy of the body moving from one body to another, from a higher body temperature to a lower body temperature. And this is due to the temperature difference. So this internal energy which is transferred from one body to another, from a higher temperature to a lower temperature, because of the temperature difference, that is called as heat. Okay, so heat is only meaningful as long as there is energy transfer, energy in transit, energy in motion. In itself, in isolation, the heat content of a body, the heat content of an object, there is no such thing. You cannot define anything like that. You cannot say I have this much heat content. You can say I have a body temperature of this much, but you cannot say I have heat content of this much joules or calories, whatever. You cannot say something like that. You have to define it in terms of temperature. Okay, so heat is always energy in transit, moving from one object to another. That is, an object from a higher temperature to an object at lower temperature. Okay, so this is heat. So once heat is transferred to a body, it becomes part of its internal energy. Okay, it increases the kinetic energy of the molecules. So some basic units of heat by which we measure it. This is the SI unit, which is joules, and the CGS unit, which is calorie. Okay, 1 calorie is 4.186 joules. Okay, so this is all about heat. So the next important thing in this heat and temperature thing is obviously temperature. So instead of making a separate video, I am combining it together so that you can understand both things in a better way, heat and temperature, because they always work in pairs. You have to always consider them in pair. So we have discussed heat. Heat is basically the internal energy of an object because of its molecular motion. Now, what is temperature? Temperature is the measurable aspect of this heat and temperature, this pair. This is what defines heat. This is what causes heat flow, energy in transit. This is what causes movement of heat. So we can say, as a simple definition, temperature is the degree of hotness or coolness of a body. That is the basic definition. But there is much more to it. When two bodies are placed in contact, as I said, there is always heat flow. Heat flow means internal energy flow. A part of internal energy of one body flows to another body. But how do you decide in which direction the heat flow, the energy flow will take place? This is what is determined by temperature. Okay, suppose we have two objects. Again, I am repeating it. Suppose we have two objects, A and another object B, and temperature TA, TB, with TA greater than TB. Here, heat will flow from A to B. Heat will flow out of A into B. As a result, temperature of TA, it will drop down, temperature of TB will increase till both TA is equal to TB. And this is called as thermal equilibrium. Okay, thermal equilibrium means the condition in both the objects, they arrive at the same temperature. When both the objects, both the bodies, they are at the same temperature level. And in this case, no heat transfer takes place. So in a way, the more proper definition of temperature is, it is the thermal state of a body which decides the direction of flow of heat. That is the internal energy, a part of internal energy from one body to another when they are placed in thermal contact with each other. This is the more proper, appropriate definition of heat. This is for kids to understand. They cannot understand internal energy and all that. But for us scientists and engineers who are more interested in the proper application, proper definition of heat, this is the more appropriate definition. Okay, this is the proper definition. The thermal state of a body which determines the direction of heat flow, the internal energy. And this is thermal equilibrium. So if you want to understand heat and temperature in a different way with some other analogy, you can visualize this. Let us say we have water flowing from the top of a hill. Okay, water always flows downhill because of the height levels. Okay, let's say we have this, like this, a sloping. Okay, this. So water will always flow like this. Okay, water will always flow like this, downhill. Why? Because of the height difference. This is at a certain height. Okay, let's say HL, and this is at a certain height. So this is the ground level, and this is HH. So obviously the height, this is higher than the lower level height. So this height difference causes the direction of water flow. So here, if we compare it with heat and temperature, height is equivalent to temperature, not the same. Analogous analogy I'm talking about. It is not the same thing. Height is the same as temperature, and water flow is the same as heat flow. Okay, this is height, this is temperature, this is water flow, this is heat flow. Height difference determines the direction of water flow, temperature difference determines the direction of heat flow. This is the mechanical analogy. If we use another electrical analogy, let's say current always flows from a higher potential to a lower potential. Okay, higher electric potential to lower electric potential. Let's say this cell, it has a voltage of VH, and this cell, it has a voltage of VL. Current will obviously flow from VH to VL because VH is greater than VL. So here electric potential determines the direction of current flow. So here electric potential is the same as temperature and current is the same as heat. So that's why heat is also referred to as heat current. Okay, and thermal, it is always also referred to as thermal potential, like that. So this is the analogy, the comparative analogy between heat and temperature and potential difference and current. Okay, so another important thing to understand about temperature is its kinetic interpretation. We know that heat is basically internal energy because of the molecular motion, vibrational, rotational, translation. So it's the velocity which causes the internal energy. Increase in velocity increases the kinetic energy, and that increases the internal energy. So we can say the temperature of a body is a measure of its average kinetic energy of the molecules. All the motions considered, 3 motions considered. When the body is heated, that is more heat is supplied, the molecules move faster. So when the molecules move faster, their velocity increases, their kinetic energy increases, and that increases the temperature of the body. So this is basically the kinetic interpretation of temperature. So here is another important thing where we have to draw a comparison between heat and temperature, because it is so interlocked, it is so connected that sometimes we can confuse one with the other. So we have to assign proper definitions, proper demarcations between the two. So basically heat is energy, internal energy, a part of internal energy of the body, because of which part of energy which travels from one point to another. Okay, it is because of the internal energy, because of the movement, random movement of molecules, considering all 3 types of motion, and this produces us in the sense, the basic sensation of hotness or coldness. Now temperature is a measure of the hotness or coldness. Like I said, we cannot say that this body has this much heat content, energy content, but we can say that this body has a temperature of, let's say, 30 degrees Celsius, 35 degrees Celsius, 98 degree Fahrenheit, like that. Okay, you get it. You have to try to understand this. So heat is the cause. This is the cause. Temperature is the effect. You know about cause and effect relationship. What causes something, and then we see the effect. So it represents the total kinetic energy of the system, heat, and temperature, it represents the average kinetic energy of the system. So always understand this. If you understand this point, cause and effect, you will understand heat and temperature. Heat is the cause, temperature is the effect. Temperature difference drives heat flow. Heat in itself, in isolation, has no meaning. It is temperature which defines heat flow. Okay, so this is heat and temperature. Next, which we'll discuss, is thermometry. So thermometry is the branch of physics which is the thermodynamics, the subcategory which deals with the measurement of temperature. So any device which can be used to measure temperature of a body, that is called as a thermometer. So it is derived from the Latin word thermo, which means heat, and meter, which is measuring device. It is self-explanatory. Okay. Now, what is the principle of a thermometer? So thermometer makes use of some sensing material, some measurable property which responds to external temperature. Okay. So that measurable property is called as thermometric property. So generally we accept linear change in temperature with the measurable parameter. So there are some different types of thermometric properties which we have discussed in sensors and transducers. If you are an engineering student, and you can watch the sensors and transducers playlist. It basically deals with this. Okay, so you will understand it in a better way. Here I will not go into detail with all that. So basically the different thermometric properties which are used is the length of a liquid column in a capillary. So here the liquid column rises and falls with rise and fall in temperature. The pressure of a gas at constant volume temperature. So all of this, it uses the relationship PV is equal to nRT, this relationship, where temperature is determined either on pressure and volume, taking either of them constant. Either constant pressure volume thermometer, constant volume gas pressure thermometer. So like that. Okay, one parameter is kept constant and the other is responding to temperature. Then we have electrical resistance thermometers, where resistance changes with respect to temperature. It has special properties, special materials are selected for this, for example platinum. Then we have thermocouple, which is the thermoelectrical EMF thermometer. It is called as thermocouple. So here the potential, the electric potential of the object, or the potential difference between the two ends of the object, they fluctuate with temperature. So here the sensing property, the thermometric property is electric potential. And then we have radiated power, which is pyrometers. All of this I have covered in sensors and transducers. If you want to understand more, you can watch that. Then we have temperature scales. So if you want to measure something, we have to define a scale for that. Only then we can measure. Okay. So let's say you say that a body's temperature is 10 degrees Celsius. So what is 10 degrees Celsius? Unless and until you know what is the base level, what is the reference level. Okay, what is the reference level? You have to measure it, you have to define it. Okay, only then you can say that this is 10 degrees Celsius. 10 degrees Celsius with respect to what? So like that. So you have to define a temperature scale. For that, two fixed points are required, two reference points, two reference levels are required. And generally those two reference levels, they are the melting and boiling point of water in the ice, water and water vapor equilibrium. So those two fixed points are generally the melting and boiling point of ice and water respectively. So once we define two fixed points, they have to be divided into certain divisions. Okay, so that defines the unit of the scale. So the temperature at which pure ice melts at standard pressure, that is chosen as the lower fixed point, and the temperature at which pure water boils at standard atmospheric pressure, that is chosen as the upper fixed point, like I said. and the two fixed points are divided into a suitable number of equal divisions, and that creates the thermometric scale. So there are different types of thermometric scales, temperature scales. One is the Celsius scale. So here the lower fixed point is taken as 0, the upper fixed point is taken as 100. 0 is the ice point, 100 is the steam point. And the interval between 0 and 100 degrees Celsius is divided into 100 equal parts. So we have each part, each division equal to 1 degree Celsius. Then we have the Fahrenheit scale, where the lower fixed point is 32 degree Fahrenheit, which is the ice point, and the upper fixed point is 212 degree Fahrenheit. So a total 212 degree minus 32, that is 180. And the interval is divided into 180 equal parts, where each part represents 1 degree Fahrenheit. Then we have the Romer scale, where the lower fixed point is 0 degree Romer and the upper fixed point is 80 Romer, and the interval is divided into 80 equal parts, and each part represents 1 Romer. And then we have the Kelvin scale, where the lower fixed point is 273.15 Kelvin and the upper fixed point is 373.15 Kelvin. So a total 373.15 minus 273.15, that is 100, and the interval is divided into 100 equal parts, and the SI unit is Kelvin. Each part is 1 Kelvin. So if you want to convert one scale to another, generally you will find Celsius and Kelvin. Mostly you will find Celsius and Kelvin, but in some cases the other two scales are used, but mostly you will find Celsius and Kelvin. So if you want to convert one scale, temperature to another, this is the basic formula. You just watch it, you can use it, where you pick temperature on one scale, whatever temperature you have, you want to convert to another scale, that temperature you keep it here, then the lower fixed point of that temperature scale divided by the difference between the upper fixed point and the lower fixed point, and then you will get the result of the temperature on the second scale minus the lower fixed point in that scale divided by the upper fixed point and lower fixed point. Okay, so this is the basic formula. So this formula you can use it to interconvert between different temperature scales. This is Celsius, okay, this is Celsius, this is Fahrenheit, this is Romer, and this is Kelvin. You can use any two, you can pick any two and use it to convert Celsius to Fahrenheit, Fahrenheit to Celsius, Fahrenheit to Romer, Romer to Fahrenheit, Romer to Kelvin, and Kelvin to Romer, or Celsius to Kelvin, or Celsius to Romer, like that, or any you can pick any two, you can make any two pair like that and find out the other one, but one of this should be known. If both of them are unknown, let's say TC, you have to convert Celsius to Fahrenheit, and both these two, TC and TF, both are unknown, you cannot convert. One of them should be known. If you know TC, you can get TF. If you know TF, you can get TC, like that. Okay, so this is the interconversion formula. Now you can watch all of this in detail. We'll discuss all of this in detail in thermodynamics also, but this is just brushing the concepts, only that much which is required for material science engineering. Okay, so here this is the thing. Okay.